Det är så att det är 1 april idag. Och det innebär att vi har ett födelsedagsbarn. Han heter Emil. Och han har sagt till mig att han gärna vill att vi sjunger för honom. Så jag undrar om alla kan ställa sig upp och hjälpa mig. Daniel, Teresa och Johnny. Emil förlåt, vi måste sjunga.
Det är riktigt eller?
Han föddes faktiskt idag.
So you are also being recorded, no problems?
Yes, that's perfect. Okay. Ja må han leva, ja må han leva, ja må han leva ut i 100:e år. Ja visst ska han leva, ja visst ska han leva, ja visst ska han leva ut i 100:e år. Ett fyrfaldigt lever för Emil, han lever. Hipp hipp. Hurra, 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 hurra!
So how old are you now?
25.
Oh, 130!
Jag ska skaffa egen försäkring.
Va? Okay, good afternoon. Let us start the lesson. So last time we talked about equivalence relations. So if you remember, just quickly, if you have a set, you multiply the set by itself by a Cartesian product, and then you get a set of ordered pairs. If you pick some of them and put them in a new set, that becomes a relation on A. But if you have 3 more properties to it, then you would call it an equivalence relation. The first one is reflexive, meaning that every element is in relation with itself. It is symmetric, means that if x is related to y, y is also related to x. And lastly, it is transitive, meaning that if x is related to y and y is related to z, then x is related to z as well. That was the definition of an equivalence relation, and we had some examples last time, but we want now to define what we called equivalence class. Okay, so let me just define it here for you. So if I give you a set, what's of course not empty here, and then I would say that R is a relation on A. What does it mean? This sentence can be simply translated as R is a subset of A Cartesian product by A, which usually we denote it by A squared. Okay, this is the meaning of R being a relation on A. And now, but here we want more. If I want to talk about equivalence classes, I need to have this relation and equivalence relations. Okay. So equivalence classes only make sense for equivalence relations, not just for any kind of relations. Okay? And then equivalence, and then let us pick one element from the set A, and I can ask what is the equivalence class of this element. Okay? And by the way, it was we had the convention that whenever we have equivalence class, according to your book, let us show the relation by this tilde. Okay, that's good. Okay, so you say that equivalence class of an element within the set according to this equivalence class. If you want to emphasize on the equivalence class as well, you equip it with a subscript of tilde here. Otherwise, if you already know which equivalence relation we are talking about, you don't need to put this. Okay? So what is the meaning of this? This is a simple thing. It means all the elements which are related to this picked element. It means all x's in your original set such that x is related to the one you picked. Yes? A very simple concept. So, for example, do you remember being a classmate is an equivalence class, is an equivalence relation. So then if I pick one of you and I ask you what is the equivalence class of that person, what is the answer? It means all the people who are related to this single person. It means all the people who are classmates to the person. So it means the group of everyone, including himself or herself. Yes? That's the meaning of equivalence class. So, can equivalence class be empty? No. No, because at least it contains the same element within itself. If you want to prove it rigorously, so for every A in A, this is something it is good to know. A always belongs to its own equivalence class. Why is that? You know, if you want to see if something is in the equivalence class or not, you have to ask the question, is this element related to this element or not? Okay, is that the case? Yes. This means that because A is related to A, because it is reflexive, so every element is related to itself, so this means that A belongs to this equivalence class. So this is always true. So none of them can be empty because at least they have one element, and that is the element here. Okay, any questions? Okay, so let us go and solve some examples. So in example 1, determine the equivalence class of pi over 3. And if we go back, yeah, I think this is a link here. Example 1 was this example. So let me write it here for you. So we did this before. So in this example 1, A was defined to be from 0 to 2 pi. And we define for all x and y in A, we define x is related to y if and only if what happens? Sine of the first one squared plus the cosine of the second one squared is equal to 1. So this is what we showed yesterday. Do you remember? We proved that this relation is indeed an equivalence relation. And then I can talk about equivalence classes of the elements within my original set. So one of them, according to this problem, one of them is pi over 3. Pi over 3 is a number in A. So I am allowed to ask this question, what is the equivalence class of pi over 3? So if you don't mind, let me put the question mark here. So this is the question. If you want, you can emphasize until the here, but because we are talking about this one, we don't need to emphasize. Okay, so how should I do that? I need to remember this definition. So this means the set consisting of all x's within A, but A is this, but such that that x is related to this element that we picked. In this case, pi over 3. So far, I have done nothing except rewriting the definition. Is that clear? Okay, in order to understand which one of them I have to choose, I have to ask myself, which one of these elements are related to pi over 3? So this means that I will take this and translate it here. So what is the meaning of x is related to pi over 3? According to this, it means that sine of the first one squared plus cosine of the second one squared, which is pi over 3, should be 1. So I am looking for all x's within this that satisfy this. Okay, so this means it is a high school problem, so you need to solve this trigonometric equation. So let me solve it here. So this becomes sine x squared. Cosine of 60 degrees is 1/2, squared is 1 over 4. Is equal to 1, so this means that sine squared x is 3/4 if I move this to the other side, and if I take the square root, it becomes plus or minus the square root of 3 over 2. So this means that if I am looking for the equivalence class of pi over 3, I have to solve this equation, but not in general, because I am only interested in elements between 0 and 2 pi. So you remember sine of which angles are the square root of 3 over 2 and minus the square root of 3 over 2? Square root of 3 over 2 is 60 degrees. Okay, so this means that x should be 60 degrees, write it in radians. Yes, pi over 3. This is not, by the way, surprising, because I told you that at least the element itself is within its own equivalence class. So that was not surprising. You could immediately understand that is going to happen. But do you remember what is the other one for sine? The other one is pi minus pi over 3, 120 degrees, which is 2 pi over 3. These two, sine x is plus square root of 3 over 2. But there is another possibility that sine x can be minus a square root of 3 over 2. So there will be two more angles. So do you remember that is trigonometry? So if this is the unit circle, so 1/2, so 3 over 2, let us say that here, this height is the square root of 3 over 2. So I will have one angle here, I will have one angle there. So one of them is 60, the other one is 120. These are these two. But for minus the square root of 3 over 2, I have to consider this angle, yes, and this angle. So this angle. But this angle is negative, so I have to, because negative is not acceptable, because I have to be from 0 to 2 pi, so I have to write it in a positive way. Yes, so let me write this one first. So what do you think this angle will be? This angle will be 180 plus 60. Yes, so it becomes 180 plus 60, which is 4 pi over 3. But this angle, I can call it minus 60. From trigonometric point of view, minus 60 is also okay, but minus 60 is not within my set. So I have to write the name of it, which is inside my set. What is that? 2 pi minus pi over 3, yes? So this becomes 5 pi over 3. So finally, if you want to write everything down, so the equivalence class of pi over 3 is a set, it's always the case, but consisting of 4 elements. Pi over 3, and the other one 2 pi over 3, the other one 4 pi over 3, and the other one is 5 pi over 3. So that's the equivalence class. But intuitively, if I ask you what is the meaning of the equivalence class of pi over 3, it means all the elements within the set that are related to my element pi over 3 from here. Yes, they are related using this relation defined in the problem. So that's a very simple idea. Yes? Any questions? Okay. So now these are examples I want you to go through them, checkpoints. These are very simple ones based on the examples and checkpoints we already mentioned. Okay, so then there is the notion of partition. And this is also a very simple idea. So when I give you a set and I ask you write a partition for your set, it means write it. So it means find subsets of A that are not empty, but mutually they don't have anything in common. Mutually they are disjoint, and the union of all of them becomes the original set. Okay, so I have written them in words for you. Okay, so let A be a set, a class or family. Usually if you have a set, within the set you have other sets. The original set is called a class or a family of sets. So you see here, usually, of course, I don't know how much you have studied set theory, but here I have a set consisting of numbers, consisting of elements. But I can have a set in which I have another set or sets. Yes, this is a set of sets. And usually the set of set is called a family or class. So if you see this word, it means that you have a set containing sets as elements. Okay? Nothing but serious here. Okay, so let A be a set, a class, or a family of sets is called to be a partition of A if none of them is empty, if the intersection between any two distinct one of the family is empty, and if you union all of them, this big cup notation means union of everything there goes back to the set itself. If you have these three conditions, then you say that I have a partition for my original set. And as usual, the examples are much easier. So if I go to the next example here, I am asking you to list all partitions of the set A equals to A, B, and 3. A, B, and C, sorry. So I have a set here, A, B, and C. I want to write all partitions. First of all, a partition is a class, is a family. So it means that if I want to write the first partition, so if you don't mind, let me call it partition number 1. Okay, so this is a set, this is a class of sets with three properties. None of them is empty. So I have to put subsets here. One subset is always empty, but according to the definition of the partition, I am not allowed to put empty there. Okay, so for example, one case is to put A here. Let me write one and then explain it for you. You will immediately understand that. So this is a partition. Why? Because first of all, all of them are subsets of my set. They are coming from my original set. None of them is empty because all of them contain exactly one element. So none of them is empty. But no matter which two of them I choose, their overlap is empty. So the intersection, the overlap, the common elements between these two is empty. The common elements between these two is also empty. The common element between these two is also empty. So it means mutually they are disjoint. This is the terminology we use. We say that these sets are mutually disjoint, nothing in common. And this is not enough. One more condition. What is that condition? When I put them on top of one another, it becomes my set. So it means that, so if you want to really write this, this is not empty. This is not empty. This is not empty. But the intersection between these two, or these two, or finally these two are all empty. And if I union all of them, it becomes ABC, which is my original set. So then I can say that this is one partition. Yes, can you give me another? The exercise is asking you write all partitions. So what is the other partition, for example? Do you think this is a partition? No, it respects two conditions. None of them is empty. The union of them is the original set, but they have some overlap. So that is not a partition. If I want to make it partition, so let me write it like this. This is partition number 2. So another partition. So you can write A and C, but with B. Yes? And by the way, it doesn't matter if you write it the other way around, because in a set we don't have order. And then the other one is what? I can put C out. No, A out. Is there any partition that I haven't written? Yes?
It's the full set of partitions.
The full set itself. That's the only one, I think. So the full set, don't write it like this. This is not correct. Why? It's a set containing this set, so that's the partition. Okay? So these are the 5 partitions of that set. The idea is very simple, so it's not very... and there is no very simple closed formula for it in combinatorics. You can do it case by case, calculating things and add them up. But there is no such a formula like the number of subsets. For the number of subsets, you say that 2 to the power of the number of elements. But for partitions, there is no single closed form for it. Okay? There are some ways you calculate it, if you have seen it in combinatorics, but not in general. Okay, so now this is a very important theorem, very easy one to prove, but it is very a deep one. It's a fundamental theorem of equivalence relations. By the way, let me test your understanding a little bit. So, do you remember we talked about this before? If I give you a set which is not empty, do you say that empty is a relation on A or not?
Yes.
Why?
Because,
Because a relation is always a subset of the Cartesian product. So if your Cartesian product is by itself, it becomes a set of ordered pairs, and if for some reason you decide not to choose any one of them, you are left with empty. So empty is a subset of A times A. So empty in principle is a relation. But can you tell me, is empty an equivalence relation?
no.
If the relation is not equal. What do you mean by
Oh, I'm asking you, I give you a set, for example, I give you this set, and I cross product it by itself, Cartesian product it by itself, and I decide not to choose any element from it. Definitely this empty is a relation. But my question is that, is this empty relation, let us do it case by case, is it reflexive?
Yes.
Is it reflexive or not? You understand what I mean? So let us make it simple. A is equal to AB. I cross product A by A, so it becomes A and A. It becomes B and B, A and B, B and A. Yes. Okay. And then, do you agree that the empty set is a subset of A cross A? Empty set is a subset of everything, so it is a relation on A. Yes? Empty is a relation on A. But my question is that, do you think empty is reflexive?
Yes.
What is the meaning of being reflexive?
It's
Every element
with itself.
from the set, from the original set, so it means that it is reflexive if A is related to A and B is related to B. But do you remember what was the meaning of this notation? This means A and A belongs to this. So it means that this cannot be a reflexive relation, yes? Because for any reflexive relation, you need A and A be in there, B and B also be in there. Yes? Understandable or not? Okay. So this is important to understand. The empty relation is an empty set is a relation, but is it a reflexive one? No, because for example, if it is supposed to be reflexive, it means every element from my set should be related to itself. Do you remember what was this notation meaning? This means that, do you remember I told you when you write A or B, it means A and B belongs to R. So when I say A and A are related, it means A and A should be within my relation. But you yourself say that the relation is empty, so nothing is there. So it cannot be reflexive. Is that right? It doesn't contain anything. But is it symmetric, empty? Is empty symmetric? It has a meaning. And the answer is yes, it is symmetric. Why is that? Exactly like, for example, why do you say that empty is a subset of A? Why empty is a subset of A? Because what is the meaning of A being a subset of B? It means everything in A is in B. Yes? That's the meaning of A subset of B. So can you define for me what is the meaning that A is not a subset of B? This means everything in A is automatically in B. So when I say A is not a subset of B, what does it mean?
Something in A is in B.
There is something in A which is not in B. That is the meaning that A is not a subset of B. Okay, but now you want to prove that this is the case.
Wait, excuse me. But you said before it's because empty is a subset of A squared, now we're talking about empty as a subset of
No, because I know what I'm doing. So you ask me about this
Yeah,
doesn't
I-
make sense. I am making a simpler example to first of all make it sense, and then I will go back to my example.
Okay.
Yes? So, empty is a subset of A. Why? Because probably every one of you know that. Yes? But why is that correct? Yes?
Because if it wasn't a subset of A, then there has to be something in the
In the empty which is not in A.
Yeah.
So that is exactly the logic behind what I am going to talk now. Okay? So now my question for you is empty was not reflexive. Yes? Because I am assuming that my original set is not empty. But is empty symmetric or not? The idea is more or less the same logic. You see, you say it is symmetric if x and y belongs to R, it is guaranteed that y and x also belong to R, to your relation. If this happens for every pair, you say it is symmetric. So now can you tell me what is the meaning of not being symmetric?
One of them is in an R. Right?
No, it means that you can find a pair which is in R, but the other way around is not in R. So empty should be symmetric, because if you say empty is not symmetric, it means you manage to find a pair in empty for which the other way around is not empty, is in empty. Is that right? Okay, think about it. The empty set, if your original set is not empty, the empty set is not reflexive, but it is symmetric, and it is also transitive. But it is not an equivalence class, equivalence relation, because it is not reflexive. Yes?
But by the definition of equivalence relation, it says for every x and y belong to A, there is no x and y belong to empty. There's nothing in empty. You cannot say when x equal to
No.
y.
This means this relation for all x px, the negation of this is that exists a p, not px. Okay?
Yeah, but
So if it is symmetric, it means for all x and y, this is what I have written for you. Yes. This is the meaning of being. This is the meaning of being symmetric.
yeah, for all x and y belong to R, right?
Belong to A.
Yeah, but now this case A is empty, so there are no x and y belong to empty.
No, for all x and y belong to this. So you need
Okay,
to.
yeah, sure, okay.
Yeah, so you need to go back and see the logic. So if you want, this is a very good question. So I mean, for all x in A, if you want to negate something like this, the negation of this means there exists an x in A such that not px. Okay, so think about this, and then we can discuss after the lesson. But anyway, so that's a very simple thing. So let us just immediately pass, because otherwise we will not be able to finish this. Anyway, so now I was telling you, okay, I was telling you something for fundamental theorem of partition. So that's a very nice theorem. It tells you that if I give you a set and I give you an equivalence relation on A, yes, then if you construct all equivalence classes and put them in a set, this set is a partition of your original set. Is a partition of A. And so what does it mean? It means that, for example, let me show you something like this. So if this is your original set, my claim is that if you pick an element from here and construct its equivalence class will be one part of the bigger set. For example, let us consider it like that. If you do it for this one inside that, the equivalence class of B and A will be the same. I will show you, okay? But if you choose something outside it, equivalence of this one will be another partition, another part of the set A, which is not empty and has nothing common with the previous case. If you consider all equivalence classes that are distinct, at the end, if you look at your original set, these will form a partition for your original set. This is what we want to show. Is that right? Is it clear what we want to do? So if you give me a set, if you give me equivalence relation on that set, I can pick elements from A and construct equivalence classes. Some of the equivalence classes, as you will see, become exactly equal. Choose one of them, put it in the back, and go and find other ones. As far as when you are finished with doing that, in your back you have a partition of your original set. So that's the mean. That's what we want to show. Okay? So how should I show that? My claim is that this class is a partition of A. What things I have to show? 3 things. I have to show none of them is empty. I have to show that any 2 of them don't overlap. And I have to show that the union of all of them is the original set. Yes? So none of them is empty. Why? We just talked about equivalence classes cannot be empty. Because if you pick this, at least it contains one element in it. So this is not empty. Okay? Now what I want to prove for you is this. My claim is that if you pick two elements from A, there are 2 extreme cases that might happen. Either the equivalence classes are exactly the same, or suddenly they have nothing in common. Okay, so this is my claim. So let me write the claim. So I want to show that if you pick 2 elements from your original set and look at the equivalence classes, there are 2 extreme cases can happen. Either they are completely equal or they are completely separate. There's nothing in between. Okay? So this means or. But I want you to learn a little bit about these kinds of proofs. How should I prove it? I want to prove or. Okay? It means either this happens or that happens or both. So the standard method, for example, if you want to say that let us go back to high school algebra. If A times B is 0, what can I conclude? I can conclude either A is 0 or B is equal to 0, yes? How do you prove this? We say that if A is 0, you agree with me, we are done. So let us assume that A is not 0, we prove B has to be 0. This is the logic. Is that clear? Is the logic clear? I want to prove that either this happens or that happens. If you agree that this happens, fight is over. But if you don't agree that this happens, I show that the next one has to happen. Then it means that at least one of them will happen. Is the logic clear? So I want to use the same logic here. I want to say that this happens or that happens. So what I would say that if the intersection between these 2 is empty, we are done. This is completely enough for mathematics texts. We are done. Because I want to show that either this happens or that one. If you agree this already happens, the fight is over, we are done. If not, we show that what happens, the class of A is equal to class of B. Okay? This is what we want to show. The logic clear? Okay. So, let us do that. This, when you say that if not means that I am assuming that A intersect B is not empty. Okay? Then what happens? It means that there exists an X. Of course, if you want to emphasize from your original set, such that X belongs to this intersection. Yes, that's the meaning. If you agree this is empty, we are done. If you disagree, it means you agree there is something in it. Let me call that something X.
Not equal to empty.
What? Not equal to empty. Thank you. Okay, so then what should I do? I would say that X belongs to A intersect B, it means X belongs to A and, this means and, X belongs to B. Yes? But can you tell me what is the meaning? When I say X belongs to the equivalence class of A, what does it mean? It means that X is related to A. That's the meaning of being in the equivalence class. And when I say X belongs to B, X belongs to the equivalence class of B, it means that X is in relation with B. Understandable what I'm doing? Yes? Okay. Now, we want to prove that, so we know this. We know that there is one element which is related to A and related to B, if you agree that this is not empty. Okay, but now we prove that the class of A is equal to B. Can you tell me what is the standard technique to prove that these two are the same? Yes?
Maybe we show that every element in.
Yes, because these are sets. This is, don't get confused. This is at the end of the day a set, and this is a set, and this is equality between two sets. So there is one trick for it. I should say that this is a subset of that, and this is a subset of this. Yes. So this means that we prove this by proving this one is a subset of B, and this one is a subset of. Okay, and if you don't mind, let me put a 1 up there and a 2 here. Okay, so proof of 1. 1. So for proof of 1, I would say let, because I have already used letter X, so let me say let Y belongs to A. We show that Y belongs to, yes? Yes, is that right? Okay, can you finish it now? It's very simple now. So I want to prove that this is a subset of this one. I pick any element from this one. I try to convince you that this element that I pick is also on the right in the right hand side. So I start from here. Y belongs to this. What is the meaning of that?
Y relates to.
Y is related to A. Yes? Okay? And then here, what I had A, X related to A, X related to A. Okay, so let me write it like this. X related to A will actually tell me A also is related to X. Why? Because this is equivalence relation and it is symmetric. And now put these together. Y is related to A is related to X. By transitivity means that Y is related to X. Is that right? Okay, but now I have one more thing here. X is related to B. So then, because X is related to B, again transitivity will help me to say that Y is related to B as well. Yes? And then what is the meaning of this? It means Y belongs to the class of B because it is related to B. Is that clear? So, yes, let me just go very quickly. My goal is to show that equivalence classes are either completely equal or completely distinct. Two extreme cases. If you believe that this is yes. So if you believe that sorry, I made a mistake. Yeah, this one is wrong. So you didn't fix me. This is equality. I want to show there are two extreme cases. Yes, either they are equal or they are completely separate. I mistakenly write something wrong. Okay, what I said is correct. What I wrote was wrong. Okay, so if you believe in this, then fight is over. We are done. If you disagree with this one, I show you that you have to agree with the other one. There is no escaping from this. So if this is not the case, it means there is something in this intersection. There exists something x in the intersection. But when x belongs to the intersection, it means it belongs to the first one and belongs to the second one. By the definition of the equivalence class, it means that x is related to A and x is related to B. But remember, this relation is an equivalence relation. So it doesn't matter if you want, you can interchange the roles because it is symmetric as well. Keep it there. And then, because we want to prove this equality is the level at the level of sets, I have to show that this one is a subset of this one and the other way around. Proof of one. In order to show that this is a subset of this one, I choose an arbitrary element from the left one, and I show that this one is definitely in the right side. So from here, by definition, I can write this. Yes? And then I go here and bring this down. Because of symmetry, I can change them. And now I combine this one with this one. Because of transitivity, y is related to A is related to x. I can conclude that this is transitivity, yes, of tilde. I can conclude that y is related to x. But again, I go up and pick this one and here. So y belongs to, y is related to x is related to b. I can conclude that y is related to b, so it means y is in the equivalence class of b. And the other proof is exactly similar, so I will not do it. So proof of 2, similar. Yes, so we are. So remember, equivalence classes are either completely identical, the same, or are completely separate. Doesn't have even one single element in common. So none of them is empty, but if they are not equal, the intersection is empty. And the last thing that I need to show is if I union all of them, it becomes the set itself. Is that clear? Yes.
How did 1 and 2 show that A is a subset of B? And
Which one?
How did
Here.
how did that show that A is a subset of B?
No, I didn't show A is a subset. The class of A, I showed the class of A is a subset of the class of B. This is proof 1. But the problem is not finished. I have to also show the other way around. And then together it means that they are equal.
Yes, but how did proof 1 show that the classes were subsets of their class?
Okay. So what is the meaning of being a subset? If I want to show that if a set is a subset of the other one, this is the standard trick. I pick an arbitrary element from the left-hand side. So if I want to show this, I would say let y belong to A, and then I will start doing some mathematics based on the problem to see if I can guarantee that this one is also in B. If I can do that, it means I have shown this is the case. Yes, was that the question?
Yes.
Okay, and this we could, because I picked one element, y, from the left side, and by this analysis argument, I was able to finally show that the same y is in the right-hand side. Yes, so this means that they are. Okay, and now the union becomes, of course, the whole set. Is that right? Yeah.
If we just prove the class A, if class A equal to class B, implicate the second scenario, isn't that the same?
This one?
Yeah, because the first condition, if class A equal to class B, then there are no intersection.
No, the intersection is the same. If two sets are equal, the intersection of a set
The
with its
intersection is empty
no,
between them, right?
a set intersect with itself is the set. A intersection A is A, not empty.
Yeah, but
Yes. So this is not something very strange. It tells you that if you pick two elements and find equivalence classes, at the end you will see either the equivalence classes are identical or there is nothing in common. Okay? But be careful, A intersect A is A, not empty. Yes? Understandable now?
Yeah.
Okay, so now why the union is the whole set? Because do you agree that when I say equivalence class of A, this is definitely a subset of set itself? Yes? So it means that every one of them at least have one of them. So when you union them, it becomes the whole set. Yeah? So that's very simple. Okay. So what the idea was this: if you give me a set, an equivalence relation on the set, if I manage to find all equivalence classes, those equivalence classes form one partition of my original set. That's called the fundamental theorem of equivalence relations. Is that clear? Yes or no? Yes. Okay. So let us go to the next one. Yeah, it means that if you have an equivalence relation naturally induces a partition on your set, exactly as we described here. Okay, and then there is a name for this set. We will see that this becomes important later. This set is called the quotient set, and it is denoted by this symbol. A quotient, I mean a fraction line, something like fraction line, and you write the relation here. Okay, so if you see this symbol, it makes sense only if A is a set and this is an equivalence relation on A. And this means the set consisting of all equivalence classes of that equivalence relation. And that is called the quotient set. Yes? So it is called the quotient set induced by the relation. Okay, so that's just the name. That is not very important now, but becomes important later. Okay, so now let us see what we have. Okay, we finished that one, and we want to start this very important lesson, which is called cosets and Lagrange theorem. It's one of the very elegant and nice theorems of the whole abstract algebra. Okay, any questions so far? So let us have the break now, and then we start this after the break. Thank you.